So in the last class we were discussing regarding this I center, how to locate an I center, and we have solved some numericals also. Yeah, good. So we have solved some numericals on how to locate I center. Okay. So we'll extend this. So before locating I centers in a mechanism, there are some basic instantaneous centers. Okay. We'll discuss about those basic instantaneous centers and then we'll go ahead. Just write down basic instantaneous centers. Basic instantaneous centers. Basic instantaneous centers. Write down first one, turning pair. Turning pair. Turning pair. So if two links are connected by a turning pair, so where does I center lie for these two links? Where does I center lie for these two links? So I can say about which point I can say you can have rotation of these two links. So I can say like this. So yesterday we have discussed about instantaneous center. Instantaneous center is nothing but whenever I say instantaneous center for 1 and 2, so it is a common point for both the bodies, such that the coincident point will have exactly the same velocity. So here there are infinite number of points on this line, infinite number of points on this link. All the points on this link will have relative velocity with all other points on this link, except this point. If you look at this point on link 2 or this point on link 1 will exactly have the same velocity. Or I can say at this point, these two links will not have any relative velocity. So at this point, both the links will have same velocity, or there is no relative velocity at this point. So I can say this is the instantaneous center of rotation for these two bodies. You can call it as I12 or you can call it as I2 or whatever it is. Okay. So that's the instantaneous center. Whenever two links are connected by a turning pair, so the instantaneous center for the two links will lie at the hinge. Okay. Next I do sliding pair. Sliding pair. Sliding pair. Sliding pair. Sliding pair. So this is fixed link and this is moving link. How to locate instantaneous center for these two links? Yesterday we have seen, you choose any 2 points. You choose any 2 points. Draw velocity vectors. Draw velocity vectors. Draw perpendiculars to velocity vectors. Okay. So I have choose 2 points A and B. So these are the velocity vectors. So if I draw perpendiculars to velocity vectors, wherever the perpendiculars meet, so that is your I center. So whenever I say the body is pure translation, so all the points will have same velocity in same direction. So if you choose any 2 points and if you draw the velocity vectors, so they will meet at infinite. So these two are parallel lines, I can say they will meet at infinite. So they will meet at infinite and there is a direction, okay? They will meet at infinite in the direction perpendicular to plane of sliding, okay? Whenever it's a sliding pair, the I center lies at infinite in the direction perpendicular to plane of sliding. Here also the same thing, you can draw velocity vectors, okay? But if you draw velocity vectors here, you will get parallel, okay? So they are rotating, right? You will get parallel like this. So you draw a line passing through tail end, and similarly you draw a line passing through head of the vectors. So they will meet at this point, okay? That's one more way. When two links are connected by a hinge, you can easily identify that. Only hinge doesn't have relative velocity. All of the points on the two links will have relative velocity with respect to their coincident points, except that particular hinge. Just slide down like this, sliding pair. For sliding pair, I center lies at infinite. For sliding pair, I center lies at infinite in the direction perpendicular to plane of sliding. For sliding pair, I center lies at infinite in the direction perpendicular to plane of sliding. I center lies at infinite in the direction perpendicular to plane of sliding. So it lies at infinite, but the direction is perpendicular to plane of sliding, okay? So try to locate instantaneous center for this case. This block is sliding in this curved path, okay? This block is sliding in this curved path. You choose any 2 points, draw velocity vectors. I'm choosing this point. So I'm drawing velocity vector. So if I choose this point and if I draw velocity vector, it will be tangential to this curved path, okay? So the velocity vector that's drawn here is tangential to the curved path at this point. So I'm choosing one more point. If I draw velocity vector here, point B. So here this velocity vector will be tangential to this curved path. So to look at I center, you draw a line perpendicular to this velocity vector. So whenever you draw lines perpendicular to the velocity vector, so they meet at center of curvature. Because these velocity vectors are curvatures for this circular path. So these are normals for these tangents. And all the normals will meet at center of curvature, okay? I center lies at center of curvature. I center lies at center of curvature. eye center lies at center of curvature. So if you want to look at eye center, you choose any 2 points, you draw velocity vectors, you draw perpendiculars to the velocity vectors, wherever they meet that gives you the eye center. Okay. Try to solve this problem. So look at instantaneous center for this case. There's a block, this block is sliding, okay? This block is sliding like this. Here also the same thing, you choose any 2 points, so draw velocity vectors, so draw perpendiculars to the velocity vectors. So I've drawn lines perpendicular to the velocity vectors. So wherever the perpendiculars meet, that gives you the eye center, okay? This is the instantaneous center. This is the instantaneous center for bodies 1 and 2, okay? So this is body 1, fixed body, and this is a moving body. This is body 2. At this instant, if you stand here, you can see that disk is undergoing pure rotation. Okay. Next item, rolling pair. Rolling pair. Rolling pair. Rolling pair. Rolling pair. Right on? Relative motion is pure rolling, okay? So for pure rolling, so where does the eye center lie? Pure rolling. For pure rolling motion, where does the eye center lie? So this disk is undergoing pure rolling motion. So whenever I say pure rolling, it's rolling without slipping. Okay, so I want to look at the eye center. You choose any 2 points and you draw the velocity vectors of the 2 points and then draw perpendiculars to the velocity vectors. Wherever the perpendiculars meet, that is your eye center. You can choose any 2 points, okay? I'm choosing this point. So here, the body is rolling, right? So since the body is rolling, all the points will have 2 velocities. All the points are rotating as well as they are also translating, okay? So yesterday we have seen that. So I asked you to take the resultant of 2 velocity vectors, okay? So this is velocity due to translation and velocity due to rotation will be in tangential direction. And this is the resultant velocity of both the velocities. So I'm choosing one more point. This is point A and this is point B. So this is velocity because of translation. This is velocity because of rotation. And this is the direction of resultant velocity. So you draw lines perpendicular to the resultant velocity vector. So I've drawn lines perpendicular to the velocity vector. So wherever the perpendiculars meet, that is your eye center. So the perpendiculars will intersect at point of contact, okay? Perpendiculars will intersect at point of contact. Perpendiculars will intersect at point of contact. In the last class we have seen, whenever a disk is undergoing pure rolling motion, whenever a disk is undergoing rolling motion, the disk has to rotate about point of contact. The disk has to rotate about point of contact. Yeah. You draw perpendiculars to the velocity vectors. So this is how you have to look at the eye center, okay? So whenever a disk is undergoing pure rolling motion, instantaneous center lies at point of contact, okay? So the disk will be rotating about point of contact in pure rolling motion. Next item. Rolling with sliding, okay? Rolling with sliding. Rolling with sliding. Rolling with sliding. So the disk is neither in pure rolling motion nor pure sliding. It's a combined motion, okay? It's rolling and sliding. The disk is rolling as well as the disk is sliding, okay? The disk is rolling and sliding. So where does eye center lie for rolling and sliding combination? If you look at this motion, this rolling and sliding, it's not a definite motion, okay? So whenever I say definite motion, pure rolling is a definite motion. So I can say after one complete rotation, I can exactly say, so where will be the position of that particular disk. So here rolling and sliding it's a combined motion, okay? I cannot exactly say when we have pure rolling motion and when we have a sliding motion. So we cannot exactly locate the instantaneous center, okay, here. So in this kind of indefinite motions, we cannot exactly look at the instantaneous center, but we can specify the region where the instantaneous center may lie. Now see here, if the disk is undergoing pure rolling motion, so I center will lie at point of contact. When the disk is undergoing pure rolling motion, I center will lie at point of contact. If I assume the disk is undergoing pure sliding, if the disk is purely sliding like this, so all the points on the disk will have same velocity in same direction. It's like a sliding pair, okay? So for a sliding pair, I center lies at infinite. So in the direction perpendicular to this line. I center lies at infinite in the direction perpendicular to this line. If it is pure rolling, it lies at point of contact. If it is sliding, it lies in infinite along the line perpendicular to this line. So what I choose is, I choose this line. I draw a line. So if you look at this line, this is the common normal for both of them. So if the disk is undergoing pure rolling motion, it lies here. So if the disk is undergoing sliding, so it lies at infinite, okay? So it lies somewhere along the common normal at point of contact. Okay. Rolling with slipping is different, Aron. This is sliding. So whenever it's a sliding, the disk is moving and all the points on the disk will have same velocity in same direction. Whenever it's a slipping, the disk will be rotating but it will not move forward. So the friction is not sufficient enough, okay? It will be slipping. That's a different case. Just write down like this. For rolling with sliding, I center lies somewhere along the common normal. At point of contact. I center lies somewhere along the common normal at point of contact. Next is rolling with slipping. Rolling with slipping. So where does I center lie for rolling with slipping? Rolling with slipping. Now see, whenever a disk is undergoing pure rolling motion, instantaneous center lies at point of contact. Whenever I say the disk is slipping in the sense it rotates about the same center but it not move forward, okay? It will be having a slip. So now the disk is slipping, instantaneous center lies at the center. So whenever the disk is rolling, instantaneous center lies here. So we say like this. So I center lies somewhere along the radial line at point of contact. For rolling with slipping, I center lies somewhere along the radial line at point of contact. I center lies somewhere along the radial line at point of contact. Okay. Rolling with sliding and rolling with slipping, these two are indefinite motions. We cannot exactly look at eye centers, but we can specify the region where the eye center may lie. Just write down like this. So for pure rolling motion, instantaneous center lies here. But if the disk is slipping in the sense it rotates, but it will not move forward. It means it is rotating about the center. For slipping, it lies at this point, center. For rolling, it lies here. So we say it lies somewhere along this line. Just write down like this. Rolling with slipping and rolling with sliding. Rolling with slipping and rolling with sliding. Rolling with slipping and rolling with sliding are indefinite motions. Rolling with slipping and rolling with sliding are indefinite motions. We cannot exactly locate the instantaneous center for these motions. We cannot exactly locate instantaneous center for this kind of motions. But we can specify the region. Where the eye center may lie. So where the eye center lies, we can specify that region, but we cannot exactly locate the instantaneous center, okay? Okay, just listen here. So I think we have discussed about this higher and lower pairs, right? Higher pair and lower pair. So whenever I say higher higher pair you will be having point or line contact. If you look at all these categories, these are all higher pairs, okay? So I have point contact between these two, I have point contact, I have point contact. So everywhere you have point contact or line contact, it is a higher pair, okay? Once there was a question in IES, the question was, so in higher pair, there will be pure rolling motion, there will be pure sliding, or there will be rolling and sliding, there will be rolling and slipping. He gives some options like that. So whenever I say higher pair, so higher pair is, so this terminology, higher and lower pairs, they are just given based on the kind of contact, okay? So there is a restriction only on kind of contact. So depending upon what kind of contact we have between the pairs, so they are given as higher and lower pairs, but there is no restriction on the type of relative motion that can happen. So it can be rolling, it can be sliding, it can be anything, okay? It can be any kind of motion. But if, as long as the contact is a point contact, it's a higher pair, okay? So for a higher pair, so if you ask me a question, where does the instantaneous center lie for a higher pair? A general higher pair, I can say this is a general higher pair. So if it is rolling, it lies at point of contact. If it is slipping, it lies here. If this is sliding, it lies here. So I say like this, for a general higher pair, so instantaneous center lies somewhere along the common normal at point of contact. It can lie anywhere, okay? This is very important. This helps in solving questions whenever you come across any higher pair inside the mechanism, okay? Just write down like this. Just write a note. For a general higher pair, instantaneous center lies somewhere along the common normal. For a general higher pair, instantaneous center lies somewhere along the common normal at point of contact. For a general higher pair, instantaneous center lies somewhere along the common normal at point of contact. For a general higher pair, I center lies somewhere along the common normal at point of contact. So in a higher pair, there is no restriction on kind of motion. It can be any motion, okay? So this is all about the basic instantaneous centers. So if you have an idea on this, we can easily look at I centers in the mechanism, okay? Next here, so we'll see how to look at instantaneous centers in a mechanism. So I'm taking a mechanism, 4-bar mechanism. So this is the 4-bar mechanism. So this is link number 1. This is link number 1. This is link number 2. This is link number 3. This is link number 4. So I want to look at instantaneous center for 1 and 2. So for 1 and 2, all the points will have relative velocity except this point. So I can say I12 lies here. So I want to look at I23. Whenever I say I23 is nothing but the common instantaneous center for links 2 and 3. So common instantaneous center for links 2 and 3, it means that, so there should be one point such that, so whether it lies on link number 3 or link number 2, it should have the same velocity. So if you look at this point, it lies on link 3 as well as link 2, and velocity of this point is exactly same when you consider on link 2 or when you consider on link 3. So I center I23 will lie here. Or in other ways, simply, so whenever two links are connected by a turning pair, the common instantaneous center lies at the turning pair, okay? So these two links are connected by turning pair over here, so I center lies here. These two links are connected by turning pair over here, so I center lies here. Whenever two links are connected by turning pair, so the instantaneous center of rotation lies there. Okay? So if you look at this mechanism, there are 4 links inside this mechanism. So with 4 links, if you see how many instantaneous centers are possible, 4 C2 instantaneous centers are possible, that is 6 I centers are possible. Total 6 instantaneous centers are possible, but we have located only 4 I centers. We have not located an I center for 1 and 3. When you stand on link 1, you can see 3 moving, but you can see that motion to be in pure rotation by standing at I13, we have not located that. Similarly, 2 and 4, there is relative motion between 2 and 4. You can see that relative motion also to be in perfect rotation by standing at I24. That's also not located. Okay? So how to locate this I24? So we have discussed methods for locating instantaneous center when one body is moving and one body is fixed. When a body is fixed and another body is moving, we can easily draw velocity vectors and we can draw perpendiculars to velocity vectors, and wherever they intersect, that is your I center. Okay, but how to locate instantaneous center for 2 moving links like this? Link 2 is moving as well as link 4 is also moving. So if I stand on this link, I have to see the relative velocity vectors on this body. I have to draw the relative velocity vectors and then I have to draw perpendiculars to them, and wherever they intersect, that gives me the I center. Are you getting my point? So I have to do that. It's a little difficult to do that. So we take the help of a theorem and we try to locate instantaneous centers. So for bodies which are moving, okay. So wherever there is a relative velocity, we call them as relative I centers. So whenever you locate an instantaneous center of a moving body with respect to a fixed body, that's called as an absolute I center. Whenever you locate an instantaneous center between two moving bodies, we call them as relative I center. This is a relative I center. These two are moving. But they are connected by a hinge, we can easily locate that. But 2 and 4 are not directly connected by any hinge. How to locate I24? So we take the help of a theorem, okay. And the theorem is Aron-Cambridge theorem. Let's start. Aron-Cambridge theorem. Aron-Cambridge theorem. Aron-Cambridge theorem. This is the theorem. So we'll see what is this theorem and then we'll try to locate the instantaneous centers in a mechanism. Okay. Yeah, yesterday we have done for one fixed and one moving. Okay. Now we'll see how to locate all the instantaneous centers in a mechanism. So this Aron-Cambridge theorem, the instantaneous center for two moving bodies, so it's based on logical reasoning. Okay. The proof for this is based on logical reasoning. So let's see here. So I'm considering three bodies. So I'm considering this is body 1, okay. This is board basically, this is fixed body. So I'm considering this is a fixed body. This is body 1. This body is fixed, this is body 1, this is fixed body. So mostly we call fixed links as link number 1. This is body 1, I can say basically the board, okay. So on this board or on this body 1, so I have one more body. So I'm calling this body 2. This body 2 is moving with respect to body 1, okay. This body 2 is moving with respect to body 1. This body 2 is moving, so I can see it is in general plane motion, a combination of translation as well as rotation. So this body is moving with respect to this body 1. So it's having some general motion or whatever will be the kind of motion. So one body is fixed and one body is moving. You can easily draw velocity vectors on this body depending upon how the body is moving. And wherever the perpendiculars intersect for the velocity vectors, that gives you I center. So you know how to locate instantaneous center between a moving body and a fixed body. So this body is moving related to this fixed body. So I have located the I center. So when I located the I center, so for bodies 1 and 2, I center is lying somewhere over here. This is the instantaneous center between body 1 and 2. So whenever I said this is I12, it means that at this instant, body 2 is rotating with respect to body 1 about this point. And body 1 is fixed, that is, I can say board. So I can say at this instant, this link 2 is rotating with respect to the board about this center. So since it is rotating about this center, so I am assuming, so it is rotating in this direction with some angular velocity. Let me say omega 2. I don't know, I'm just assuming the direction of rotation, okay? So depending upon the velocity vectors, we can have different directions of rotation. Yesterday we have discussed some problems, right? So a ladder sliding in the corner of a wall, so depending upon the velocities, so we have given a direction of velocity vector. Similarly here also. So this is a fixed body and this is a moving body. So between a fixed and moving body, we can easily look at instantaneous center. We located this instantaneous center. So at this instant, this body 2 is rotating with respect to the board about this point. So with an angular velocity omega 2. So similarly, so there is one more body here. This body is also moving with respect to the board. This body is also moving with respect to the board. I can say one more, but third body. This body is also moving with respect to body 1, or I can say this body is also moving with respect to the board. It's in general plane motion. So for this body also, you can look at instantaneous center with respect to the board. So I will look at the instantaneous center with respect to the board. That is I13. I13 is lying somewhere over here. It can lie anywhere, okay? Wherever the perpendiculars meet, it lies there. The perpendiculars are meeting here, it lies here. So at this instant, link 3 is rotating about this point. So at this instant, link 3 is rotating with respect to the board about this point. So I am assuming it's rotating with some angular velocity. I am assuming it's omega 3. So this body is rotating in this direction and this body is rotating in this direction. If you can see here, so the two bodies are having relative velocity. There will be some relative velocity. So as they are rotating in two different directions. Even if they are rotating in the same directions, if their velocities are different, there will be relative velocity. Okay? So just to avoid that confusion, I am assuming they are rotating in opposite direction and their velocities are different. So there will be relative velocity between links 2 and 3. So since there is relative velocity between 2 and 3, the relative motion between 2 and 3 can also be seen to be in perfect rotation. by standing at some point. So that's called as I23. So where does this I23 lies? Where does this I23 lies? I don't know where I23 lies, but I am assuming I23 is lying somewhere over here. I don't know where does I23 lie, so I am assuming I23 lies somewhere over here. I23 is lying somewhere over here. So I23 is common instantaneous center for body 2 and body 3. So it can lie on body 2 or it can lie on body 3 or it can lie outside both the bodies. We have seen that discussion yesterday. So whenever you look at eye centers for two bodies, it can lie on body 1 or body 2, it can lie outside both the bodies, wherever the perpendiculars intersect. So here, so this is the eye center for two bodies. I don't know where it lies, I'm just assuming it may lie here. Okay. Now see here, I'm considering this eye center I23, I'm assuming this I23 lies on body 2. So we'll see what happens if I23 lies on body 2. If I23 lies on body 2, you can see body 2 is rotating with respect to the board about this center, right? So body 2 is rotating about this center. Body 2 is rotating about this center. I23 is a point on this body. So if I draw a line perpendicular to this line joining, so this is center of rotation. So this point, if you see, this is the radial line, okay? So at this instant, this link 2 is rotating about this point. So this is the radial line. If you see velocity of this point, velocity will be perpendicular to the radial line. So this will be the direction of velocity of I23 if I consider it lies on body 2. So velocity of I23 will be perpendicular to the radial line. So when I consider I23, if it lies on body 2, so velocity of I23 should be in this direction. Now see here. So if I consider I23 is lying on body 3, if I assume I23 lies on body 3 is rotating about this point. This is center of rotation of body 3. Velocity of I23 will be perpendicular to this radial line. So this is the radial line. This is center of rotation of body 3. If I assume I23 lies on body 3, velocity of I23, so if it lies on body 3, it should be in this direction. It's perpendicular to this radial line. So yesterday we have looked at instantaneous centers and we have seen some properties for instantaneous centers. That is, I told you that instantaneous center, whenever I say some point is instantaneous center for two bodies, so instantaneous center is nothing but it is that point on one body which has zero relative velocity with respect to a coincident point on the other body. Yes or no? So there may be different bodies are moving like this, but you can have one point such that, so velocity of that point on body 1 and velocity of that point on body 2 will be exactly the same. Or I can say, so the coincident points, so they should not have any relative velocity. That's an eye center. Yes or no? So, but if you look at this one, when I consider this point on body 2, its velocity is in this direction. When I consider the same point on body 3, its velocity is in this direction. So I can say this is not the eye center, right? Because this point has two different velocities. When I consider on body 1, it's having some velocity. When I consider on body 3, it's having some velocity. So I can say at this point, so if I take a point on body 3, and if I take a coincident point on body 2, there are relative velocities. So I can say this is not the point. So the same point is having two different directions. So velocities in two different directions, which is not possible, okay? A single point cannot have two different velocities. So I can say our assumption is wrong. The instantaneous center of rotation is not lying here. What I do is I try to bring this center down. When I pull this down on line joining these two centers, I'm drawing a line passing through these two centers. So I've drawn a line passing through these two centers. Now see here. So if I pull this point down, so if I say I23 lies here, now you can see here, if I consider I23 lies on body 2, what will be the direction of velocity? So for body 2, this is center of rotation, so this is the radial line, so this is perpendicular to the radial line, so this will be the direction of velocity of I23. So it is rotating in this direction, counterclockwise, so velocity of I23 will be like this. Similarly, if I assume this point lies on this body 3, so this is center of rotation of body 3, this is the radial line, so this is perpendicular to radial line, so velocity of I23 will be perpendicular to the radial line. So velocity of I23, if it lies on body 2, it's perpendicular to this radial line. If I assume I23 lies on body 3, it is perpendicular to this. You can see both. So when I consider it on body 1 or body 2, it's having the same direction, yes or no? So I can say like this, your I23 will lie on this line. Your I23 will lie on this line. And if you want to know where exactly it lies, So I can say velocity of this point when it lies on body 2 should be exactly same as velocity of this point when it lies on this body. So here you can see, you can think that it's not lying on body 2 or it's not lying on body 3. But why are you saying it lies on body 2? So what I mean is, so the body 2 shape is like this. So it's not lying on body 2, okay? If you extend body 2, the body 2 shape was something like this. If the shape of body 2 is something like this, then you can see I23 will fall on body 2. So what will be velocity of that point? Similarly, so velocity of I23, if you extend this body 3, this is the shape of body 3. If I extend body 3 like this, this is the shape of body 3. I have changed the shape of body 3. So when I change the shape of body 3, you can see this is the shape of body 3. When I extend the body 3 such that I23 is falling on that, now you can find the velocity of this point if it lies on body 3. So the two velocities should be same. So basically I can say, so if you take the shape of body, this is body 2, there are infinite number of points on body 2. So this is body 3, there are infinite number of points on body 3. All the points on body 3 will have relative velocity with respect to the coincident points on body 2, except this point. If you see this point on body 3 and a coincident point on body 2, at this point there is no relative velocity. Whereas all other points, if I take this point on body 3, it will have some velocity, and coincident point on body 2, it will have a different velocity. So whereas this point, so velocity of this point, if I consider on body 3, and velocity of the coincident point on body 2 will also be exactly the same. That's what we have seen, right? I center. So I can say like this, the conclusion is that, so whenever three rigid bodies like this, whenever three rigid bodies have relative motion among themselves, and whenever you try to locate the three eye centers, they will be lying on a straight line, okay? They will be lying on a straight line. So, and they will be lying on a straight line, and where exactly this lies in such a way that velocity of this point is same whether this lies on this body or whether this lies on body 3. So what is velocity of I23 if it lies on body 2? Velocity of I23 if it lies on body 2. Velocity of I23, velocity of this point, if I cancel it on body 2 is rotating with omega 2 velocity. This is center of rotation of body 2. This is center of rotation of body 2. I want to find out velocity of this point. This is radius, okay? Velocity of any point on a rotating object is r times omega, right? Velocity is r omega. So this is r and that is omega. So velocity of I23 is r times omega. R is I12, I23 times omega is omega 2. Similarly, if you assume I23 lies on body 3, I23 if I consider on body 3, this is center of rotation of body 3, this is the radius of rotation. So radius is, so the distance between I13 and I23, this is the distance, multiplied by angular velocity of this link. So this I23 will lie on the line joining two eye centers at such a location that these two velocities, velocity of I23 when you consider on link 2 or velocity of I23 when you consider on link 3, it will be exactly the same. It will be exactly the same. And I can say like this, so if you ask me a question, so whether this eye center lies closer to this one or closer to this one, it depends upon this omega values, okay? If I say omega 2 is more, this product should be same, right? If omega 2 is more, so I can say this should be less. So if omega 3 is less, this should be more. The product of these two and the product of these two should be exactly the same. So if omega 2 is more, the distance between these two should be less. So the distance between I12 and I23. So I12, I23 should be less, so it should lie very close to this. If omega 3 is more, it should lie close to that. So when you multiply this omega 3 with the radius, so r omega should be same. If this omega is more, r will be less for this. If this omega is less, r will be more, so that r times omega is same for both. It lies at that. Okay, I hope you understood. And one more thing, let's listen here. So here I assumed both the bodies are rotating in opposite direction. Both the bodies are rotating in opposite direction. Whenever both the bodies are rotating in opposite direction, the common eye center will lie in between both the eye centers, okay? But whenever they are rotating in same direction like this, if I assume omega 3 is in this direction, if I assume omega 3 is in this direction, but where it lies? If omega 3 is in this direction, now you can see if I consider this point on body 2, So this is center of rotation of body 2, this is radial line. So body 2 is rotating in counterclockwise direction, velocity vector will be perpendicular to the radial line in that direction of rotation. So when it lies on body 3, if I assume I23 on body 3, this is center of rotation of body 3, this is the radial line, but body 3 is rotating in counterclockwise direction, so velocity vector will be in this direction, okay? Velocity vector should be perpendicular to the radial line in the direction of rotation. So I can say when I consider on body 2, velocity vector is in this direction, when I consider on body 3, it's in this direction. So whenever they are rotating in the same direction, the eye center will not lie in between, eye center will lie outside, okay? Outside both the eye centers. It may lie here, it may lie here. If it lies here, you can see this is center of rotation, this is the radial line, so this is perpendicular to the radial line as it is rotating in counterclockwise direction. If it lies on body 3, this is center of rotation of body 3, this is the radial line, this is perpendicular to the radial line as it is rotating counterclockwise. Either it may lie here or it may lie here. Even it lies here, so velocity, if it lies on body 3, it will be in this direction. If it lies on body 2, it will be in the same direction. But whether it lies to the left or right, it again depends upon this omegas, okay? If omega 2 is more, so the distance between I12 and I23 should be less, right? So the distance between I12 and I23 should be less, so it lies on the left side. If it lies on the left side, the distance between these two will be less, and the distance between these two will be more. If it lies on the right, it means that the distance between these 2 points is less, so I can say omega 3 is more. So it depends. Okay. So basically, I just took 2 bodies and I assumed eye center lies somewhere over here. But eye center is a point where you will have same velocity when you consider body 1 or body 2. But this point is not satisfying that particular condition. When I make this point down on the line, so it is satisfying the condition. It's satisfying the condition that velocity of this point will be same when you consider on this body or this body. So we say it lies on the line joining both eye centers. Or in other words, when 3 bodies have relative motion among themselves, the 3 eye centers formed from them will be collinear. And there is no restriction on this whether the 3 bodies are connected or not connected directly. Okay, so I never considered any connection between them. Okay, so they can be connected or they may not be connected. There is no restriction on that. Just write down like this. Just the statement is enough. Okay, for GATE. If you understand the statement, it's more than enough. Just write down the statement like this. Aron Theorem. If three rigid bodies have relative motion among themselves, if three rigid bodies have relative motion among themselves, if three rigid bodies have relative motion among themselves, if three rigid bodies have relative motion among themselves, if three rigid bodies have relative motion among themselves, then the three eye centers formed from them, will be collinear. If three rigid bodies have relative motion among themselves, then the three eye centers formed from them will be collinear. Next item. The three links are rigid bodies. The three rigid bodies may be connected directly or may not be connected. The three rigid bodies may be connected or may not be connected directly. So there may be connection between the three bodies or there may not be any connection between the three bodies. Okay. If three rigid bodies have relative motion among themselves, then the three eye centers will be collinear. Okay. If you pick any three bodies in a mechanism, if there is relative motion among the three bodies, so there will be the three eye centers formed from them will be collinear. Okay. This is Aron theorem. Next, add one more statement. So whenever you encounter a case where the three eye centers are not collinear, it means that there is no relative motion among those three links. Okay. So 1, 2, 3. So this is I12, this is I23, this is I13. So you can see the three eye centers, they are not collinear. Okay. The three eye centers are not collinear. So whenever the three eye centers are not collinear, so it means that there is no relative motion among themselves. So if there is relative motion, the three eye centers should be collinear. Just write down like this. If the three eye centers are not lying on the same line, If three icenters are not lying on same line, if three icenters are not lying on same line, it's called a structure. It's called a structure. So 2 and 3 may overlap, they may not overlap. That's what I wanted to say. They may be connected. The shape of the body may be different, but when you extend the body such that the icenter falls on this, then you find velocity at that point. Okay. So you understood Aron-Condis theorem? Yeah. Okay. So now with the help of this theorem, we'll try to look at the instantaneous interest mechanism.